Good morning, all. Today we discuss the next topic from the laser physics. Today we discuss the theory proposed by Einstein. The topic is Einstein coefficients. Einstein's theory of absorption and emission of light by an atom is based on Planck's theory of radiation. And also, he used the Boltzmann distribution law. We know that under thermal equilibrium, the population energy levels obeys the Boltzmann distribution law. In the statistical mechanics, you will learn about the Boltzmann distribution law. And the Planck's theory of radiation is familiar to you in quantum mechanics. It will also discuss in the statistical mechanics also. So, in the previous session, we discussed about the absorptions and emission of light taking place between a two-level energy system. In that case, we discussed the induced absorption and spontaneous emission and stimulated emission. Okay. In the induced absorption, we discussed we obtain an equation for the number of atoms undergoing absorptions per unit time per unit volume from level 1 to level 2 as gamma 12 is equal to B12 N1 U of nu. Okay. And in the spontaneous emission, we obtain an equation for the number of atoms making spontaneous emission per unit time per unit volume as U21 is equal to A21 N2. And in stimulated emission, we obtain the number of stimulated emission per unit time per unit volume will be gamma 21 is equal to B21 into N2 U of E. Okay. So we discussed induced absorption and stimulated emission and spontaneous emission. Okay. Now, at thermal equilibrium between the atomic system and the radiational field, then the number of upward transition must be equal to the number of downward transition. Okay. Here we taking a two level atomic system. In that we consider two energy levels, that is the upper is E2 and the lower is E1. Okay. Then at thermal equilibrium between the atomic system and the radiational field, the number of upward transition means the transition from lower to upper must be equal to the number of downward transitions. Here this is upward transition. Okay. And this is downward transition, and this is also downward transition. Okay. Then the upward transition must be equal to downward transition. There is two downward transition, so we take total. Then the number of upward transition, we represent it as gamma 1 2 must be equal to U of 21 plus gamma 21. Okay. Because we know that at thermal equilibrium between atomic system and the radiation field, the number of upward transition must be equal to the number of downward transition. Then in the emission, there is two types. First is spontaneous and the second is stimulated. Then the total transition, downward transition, must be of spontaneous or maybe stimulated. So the total downward transition must be sum of these two. Okay. Then gamma 1 2 must be equal to U21 plus gamma 21. Okay. So we have the expressions for gamma 1 2. Gamma 1 2 is equal to what? Gamma 1 2 is equal to, we know that it is equal to B 1 2 N1 U of E. Okay. And the number of spontaneous emission is given by, it is equal to A21 N2. And what is gamma 21? Gamma 21 is the number of stimulated emissions, that is equal to B21 N2 U of E. Okay. Then we can write the expression as B12 N1 U of nu is equal to A21 N2 plus B21 N2 U of nu. Then this expression is arranging to obtain U of nu. Okay, we have to obtain an expression for U of nu. We have to obtain an expression for energy density. Then we collect these two terms into one side and we obtain the expression for U of nu as U of nu is equal to what? Okay, U of nu must be equal to, it will be equal to N2 A21 divided by N1 B12 minus N2 B21. Okay, and from the denominator we taking B21 outside. Okay, we taking B21 from the denominator. Okay, then B21 into the denominator sorry, we taking N2 B21 outside. Okay, so first we taking N2 B21 outside, then from the second term N2 B21 is taken outside, and in the denominator the quantity must be equal to the numerator, it is N2 A21 divided by, in the denominator, N2 B21 into, in brackets, as here only N1 B12 N1 B12 then divided by B21 N2 then minus 1, and here we cancels N2, then the result become A21 divided by B21 into B12 by B21 into N1 by N2 minus 1. Okay, here the N1 by N2, it is the ratio of populations. Okay, that ratio can be obtained using Boltzmann's equation. According to Boltzmann's law, the number of atoms according to the Boltzmann's law, can be simply written as the number of atoms in a particular energy level E can be written as N is equal to N0 E raised to minus E divided by KT, minus E divided by KT. Okay, here E is the energy of a particular level and N0 is the number of atoms in the ground state and T is the temperature. Here K is known as the Boltzmann constant. Okay, so using Boltzmann law, N is equal to N0 E raised to minus E divided by KT. Here N is the number of atom in the energy level E. Okay, so we can obtain an expression for N1. What will be the expression for N1? N1 can be written as N0 e raised to minus E1 divided by minus E1 divided by KT. Okay, and N2 must be equal to what? N2 must be equal to N0 e raised to minus E2 by KT. Then we can obtain an expression for N2 by N1 or N1 by N2. N2 by N1 must be equal to what? From this one, we can obtain using Boltzmann distribution. We can obtain N2 by N1. Using this one, what will be the result? It is equal to minus of E2 minus E1 divided by KT or KBT. KB is the Boltzmann's constant. Then we know that E2 minus E1, that must be equal to H nu. It is obtained from the previous discussions. Okay, then N2 by N1 is equal to e raised to minus H nu by KBT, or N1 by N2 is equal to what? E raised to H nu divided by KT. So for N1 by N2, we substitute e raised to H nu divided by KT. Okay, H nu divided by KBT. Okay, then the expression becomes U of nu is equal to A21 divided by B21 into B12 divided by B21 e raised to H nu divided by KBT minus 1. Okay. From the Planck's distribution law, we have an expression for energy density. U of nu d nu. It is equal to what? It is a famous expression. U of nu d nu is equal to 8 pi h nu cube divided by c cube into h nu into 1 divided by e raised to h nu divided by kbt minus 1 into d nu. Okay, it is the Planck's distribution law. U of nu is equal to energy density. U of nu is equal to 8 pi h nu cube divided by c cube into 1 divided by e raised to h nu divided by kbt minus 1. Okay, so this is the energy density per unit frequency interval. Okay, and it is also the energy density. So comparing these two equations for the energy density, we can obtain When comparing these two equations, we can obtain A21 divided by, look at the expressions. This is the bracketed one. In the bracketed term, only e raised to h nu divided by kbt minus 1. Okay. And here b12 divided by b21 e raised to h nu divided by kbt minus 1. And so first we can write b12 divided by b21 must be equal to 1. Okay. b12 divided by b21 is equal to 1. That means b12 must be equal to b21. Let it be b. Okay. That quantity is taken as b. We obtain the result that b12 must be equal to b21, and let we take it as b. Okay. Then this quantity is taken as, when we comparing, we take this is equal to, here there is no quantity, then it is equal to 1. Then b12 is equal to b21 and it is taken as b. And then the remaining quantity, the quantity outside the bracket, look at this one, a21 divided by b21. For that, the remaining quantity is equal to 8 pi h nu cube divided by c cube. So we can say that a21, or that is equal, that is taken as a, that is equal to what, h pi h nu cube divided by c cube into b21. We taken a21 divided by b21 is equal to what, 8 pi h nu cube divided by c cube, or we write a21 is equal to 8 pi h nu cube divided by c cube into b21. Here the coefficients a and b, that coefficients is called as Einstein coefficients, which accounts for spontaneous and stimulated emission probabilities. And when we finding the ratio of number of spontaneous to stimulated emissions, it will be equal to e raised to h nu divided by kbt minus 1, because we know that the number of spontaneous emission, that is u21 is equal to a21 into n2. Okay, stimulated emission u21 is equal to a21 a21 into n2, and number of stimulated emission is equal to b21 into n2 u of. Okay, then the ratio of this quantity is equal to what, n2 n2 cancel out, then a21 divided by b21. What is a21 divided by b21? a21 divided by b21 is equal to what? It is equal to 8 pi h nu cube divided by c cube, that quantity divided by u of nu. Okay, In the expression of u of nu, this quantity cancel out. 8 by h nu cube divided by c cube cancel out, and the denominator in the u of nu, it will go to the numerator. So the ratio that is equal to e raised to h nu divided by kpt minus 1. It is the ratio of number of spontaneous to stimulated emission. So when we looking at this quantity, it is the ratio of spontaneous emission to the stimulated emission. Okay, number of spontaneous to the stimulated. That ratio, we checking that ratio. When the ratio is greater than 1, when the ratio is greater than 1, then stimulated spontaneous emission must be greater. Okay, when we checking this quantity, okay, when the frequency nu is greater than, when the frequency nu is very greater than kpt divided by h, here we say that when nu is greater than kpt divided by h, very greater, then this power of the exponent is very high. Okay, then the value of r will be very greater. So the number of spontaneous emission far exceed the number of stimulated emission at thermal equilibrium. Okay, so at thermal equilibrium or at normal situations, the spontaneous emissions is greater. Okay, then to achieve laser action, more atom to be placed in the excited state, or the stimulated emission must be greater than spontaneous emission. In that case, laser action occurs. Okay, now we discussing such a situation, that is n2 is, we making n2 is greater than n1. It is the basic principle of laser action, that is population inversion. From the Boltzmann equation, we obtain n is equal to n0 e raised to minus e divided by kbt. Okay, here n is the number of atoms in the energy level E, or we call it as, it is the population in the level E. Okay, and using that condition, we obtain N2 divided by N1 by N2 is equal to what? N1 by N2 is obtained as e raised to h nu divided by kBT. We obtain N1 by N2 is equal to e raised to h nu divided by kBT. Okay. Then from this condition, we considering n is equal to n0 e raised to minus e by kBT. At n is the population in the energy level E1. Sorry, energy level E. And N1 is the population in the energy level E1. So when we looking at this equation, we can say that the ground state is more populated. Or when we looking at this equation, we can say that N1 is most populated than N2. Okay. Then if by some means most of the atoms are initially excited so that there are more atoms in the higher energy state E2 in the lower energy state E1. Then we have N2 is greater than N1. Okay. By any means, giving energy to the system by any means to send the atoms from lower energy to higher energy. So more atoms will go up. Then the number of atoms in the excited energy will be greater. So achieving such a condition, that is N2 greater than N1. This is called as population inversion. Usually at thermal equilibrium, the number of atoms N2 in the upper level, population at higher energy level state is much lesser than the population in the lower energy level. That is N1 is greater than N2. And the phenomenon of making N2 greater than N1 is known as population inversion. Okay. So population inversion creates a situation in which the number of atoms in higher energy state is more than that in the lower energy state. The method of raising an atom from lower energy state to higher energy state is called pumping. The term is familiar, pumping, pump. What is the need of a pump? In our daily life, we use water pumps for pumping water from well to our water tanks. Okay, any similar one. Here it is energy pumping. Energy is giving to atoms in the lower level, and the atoms are excited into the higher energy levels. So the method of raising atoms or particle from lower energy state to higher energy state is called pumping. This can be done with a number of ways. Okay, the first one is optical pumping, where the atoms are excited by illumination of light, and the second is excitation by collisions, and the third is the injection of carriers by forward current through a p-n junction in the case of semiconductor, and the fourth one is excitation by electric discharge, and the fifth one is excitation by chemical reaction. These are some method of pumping. In our syllabus, we discussing some laser system, and in that some of this pumping were discussed. Here the conditions of population inversion. By population inversion means the population in the higher level must be greater than the lower level. So there must be at least two energy levels, and E2 must be greater than E1, and there must be a pumping source or a source to supply energy to the medium. And the third condition is the atom must be continuously raised to the excited state. This is the condition to be achieved for population inversion. And in the case of a two-level system, when the atom is excited by the irradiation or irradiation with light or by electron collision, the number of atoms in the upper level will increase because of the pumping. But at the same time, the probability of de-excitation that brings these excited atoms back to the lower level, it will increase with incident light or electrons. Okay, it says that consider a two-level system, that is only two energy levels. E1 is the lower energy and E2 is the upper energy. Then using pumping. Pumping means giving energy to the atom in the lower level. Then through pumping, the atoms will be excited to the upper level. Then what happens? N2 increases. If the number of atoms in the excited state increases, U21 and gamma 21 must increase. U21 is the number of spontaneous emission and gamma 21 is the number of stimulated emission. That will also increase. It is a process of de-excitation or emission. So in the two-level system, the achievement of population is very risk. So it cannot be achieved. So obtaining population inversion, a system must be with at least with 3 energy levels. Therefore, 3 or 4 level atomic systems must be used for achieve population inversion. And it is not always necessary that the energy levels concerned should be discrete and sharp. The band level may be used for achieving population inversions. It is the case of dye lasers and semiconductor laser. Okay. Now we go into an important term, that is metastable state. Normally, the excited atoms have a short lifetime. Lifetime means the time they spend in a particular level. Okay. So the excited levels is not stable. So the atoms have a short lifetime. So they release their energy in a matter of nanoseconds through spontaneous emissions. Normally, a short lifetime, approximately nanoseconds. So they will release their energy through spontaneous emission. So it means that the atoms do not stay in the higher energy state for absorbing any photon. So stimulated emission cannot be occur. In some systems, some energy levels having more lifetime is occurring. Such state having much longer lifetime. That is called metastable state. A metastable state is such a excited state having longer lifetime. And a metastable can be readily obtained in a crystal system containing impurity atoms. In such type, these levels lie in the forbidden gap of the host crystal. Okay, so at a metastable state have more lifetime. So the atoms can wait there for some long time. By the term long time, it is not greater than 1 second or etc. It is 10 days to 10 days to minus 4 seconds. A metastable has lifetime only up to 10 days to minus 4 seconds. Okay. When we compare it with nanosecond, it is very greater. Okay. If there is no metastable state, there could be no population inversion and hence no laser action. So to produce a laser, population inversion is compulsory and metastable state also compulsory. It is a need. And we will on I stop here. We will discuss the different types of laser in the next session. The lasers are mainly classified as solid state laser, gas laser, liquid laser, and dye laser, and semiconductor laser, etc. We will discuss in the next session. Okay, thank you.